chapter 30 before moving on. Okay, so please enter the Kahoot. Okay, so enter 1000, sorry, the Kahoot number is 251-8872. Okay, so while you're joining, let me post the problem. Okay, so let me read it in case it's not clear. Okay, so we have a metal rod is forced to move with constant velocity v along two parallel metal rails connected with a strip of metal at one end. Okay, the magnetic field of B.35 Tesla points out of the page. Okay, if the rails are separated by a distance L 25 centimeter and the speed of the rod is 55 centimeters per second, what is the EMF that is generated? So you are this is question A. Question B, if the rod has a resistance of 18 ohms and the rail and connector have negligible resistance, what is the current in the rod and at what rate is the energy being transferred to thermal energy? So here you're asked to answer question C. Question C, at what rate? So here we're asking about the power. Okay, question C. So I will give you 3 minutes for this one. 3 minutes. Can work together. I don't know if I can magnify this. Let's see. Oh, here. Okay, so yeah, we can magnify it. Yes. The code is the code is 251-8872. 251-8872. Okay, so ready? Give you a few more seconds, 15 or 30 seconds. Okay, for the sake of time, because we have only 50 minutes today, so choose between A, B, C, or D. Huh? So I'll, yes? نعم? Yeah, sorry about that. So, yeah, choose, ignore D, I guess. Ignore D. Okay, so I will start the Kahoot. And okay, whoa, only one correct answer, huh? All right, so let's look at this problem. All right. Okay, so here we have the bar is moving at the speed of v, and we have already determined that, remember, the induced EMF is minus the derivative of the magnetic flux with respect of time, and we have seen that before it gives us minus BLV, okay? So the induced EMF, so if I want to adjust the magnitude, it's BLV, okay? And so this is the induced EMF, okay? If the rod has a resistance of 18 ohms, what is the current in the conductor? So we have I is just equal to the induced EMF divided by the resistance, which is BLV divided by R, okay? At what rate is energy being transferred to thermal energy? So remember, we have the resistance R for this loop, okay? And we can either use Ri squared, V squared over R, or V times I. Remember, V now in this case is the EMF, E times I. Any of them will give the same results, Ri squared here. So I can use Ri squared. So this will be, Ri squared is going to be R times B squared L squared V squared divided by R squared. So the square here will go and you get the power. And if you do that, the result is, okay, so for the voltage you find that it's, so this should be really the absolute value, okay, is 48.1 millivolt. The current is 2.67 milliamps, and the power is 12.9 milliwatts. Oh, that's why, because, sorry, yeah. So it was D, and I know some of you chose A. So those who chose A, that you are also correct. Sorry about that. Sometimes I make a mistake in the Kahoot. Next problem. So, well, actually 13 plus 1 are correct. So we have 14 that are correct. All right, so next problem. So obviously the scores are not going to be correct this time. Okay, so here is an interesting problem where we use the general form of Faraday's law. Okay, and we want you to calculate this at what instant? Sorry. So here, let me read it. Within the green dashed circle shown in this figure, the magnetic field changes with time according to the expression of 2t squared. Let me magnify this. 2t cubed minus 4t squared plus 8, where b is in Tesla, t is in seconds. And the radius, capital R, is 2.5 centimeter. When t is equal to 2 seconds, calculate the magnitude and the direction of the force exerted on the electron located at point P, which is at a distance r 5 centimeters from the center of the circular field region. So imagine at point P we have an electron. What is the magnitude of the force, and determine the direction. Is it clockwise or counterclockwise? So this is a good. So we'll 3 minutes for this one. So this is the general form of the Faraday's law, which is the integral over closed loop of E dotted ds is equal to the derivative of the flux, magnetic flux. Yes. نعم. The pin. It's 251-8872. 251-8872. Half a minute. Okay. Raise your hand if you're finished. I'll give you another half a minute. Okay, so choose between A, B, C, or D, and you'll have another 20 seconds. And you start. Okay, all right, so 3 correct and the rest are incorrect. So let's look at this problem here. Okay. So here we are giving the magnetic field, okay, and it's into the page, okay, and the radius r is 2.5 centimeter, t is equal to 2 seconds. Calculate the magnitude and direction of the force exerted. So first of all, we have to determine what is the electric field. We know a changing magnetic field will induce an electric field, okay, and this is given by Faraday's law that says E dotted with ds around a loop is equal to the derivative of the flux with respect of time. Okay, so here because of the symmetry of the situation, let's take a loop. Let's take a circle of radius r. So this is a circle of radius r, okay, and it passes by point P, okay, and we're going to evaluate. We know the electric field is going to be parallel to ds, so this integral here simplifies to E times the integral of ds, which is the circumference of this circle. So this is 2 pi r, okay, is going to be equal to the derivative of the flux. So now the flux is the derivative with respect of time of the integral of B dA, okay. So here the area is not changing. The area is going to be the area of this whole thing here, because that's where we have the magnetic field, okay. So this is going to be pi r squared, okay, and we have the derivative of B, so the derivative of the magnetic field with respect of time, okay. So here notice we are solving for E, so we can write E is equal, so the pi's will cancel and we will have r squared divided by 2 small r, okay. Remember, the small r is the radius that is outside actually the capital R, okay, times the derivative of the magnetic field with respect of time. The derivative of the magnetic field is going to be 2 times 3, that's 6 t squared minus 8 t, 4 times 2 t, okay. So we replace this at t equal to 2 seconds, so at t equal to 2 seconds, so this is going to be 0.25 10 to the minus 2, this is the radius squared, divided by 2 times r, which is 5 centimeters, so this is 0.05, okay, and times 6t squared, so that's t is equal to, so that is 4, so that's 24 minus 16, that's 8, okay. So when you do that, I think here I made a mistake of we don't need the negative sign here, okay. So we find that the electric field is going to be 0.05 newtons per coulomb, so this is 0.05 newtons per coulomb, okay. Now I have to determine what is the obviously the force is just QE, so we know the force is going to be Q, the charge of the electron times E, but we need to determine the direction. So first of all, I need to determine the direction of the electric field. What do we know? We know Lenz's law says that the induced electric field, or the induced is going to be opposing the change that is already existing. So here we have a magnetic field that is into the page, but is it increasing or decreasing? Okay, so notice at t equal 2 seconds, this p is going to be increasing because 2 to the power 3 is 8, so 16. So this p is increasing here. Okay, so that means the induced magnetic field has to oppose this. The induced magnetic field has to oppose this. So let me use a red color. So the induced magnetic field has to oppose this. So it's going to be out of the page, okay, out of the page. In order for it to be out of the page, okay, what is the induced if there was a loop, if there was a current? What would be the direction of the current? So in order for it to be out of the page, if I put my thumb along this loop, okay, and do this is coming out of the page. So the induced EMF is going to be in this direction. So let me call if there was a loop. So this is the induced EMF or induced also same direction as the current. Okay. If the current is moving in that direction, and we know current is positive charge, the negative charge is going to be moving in the opposite direction. Since we have an electron here, so the electron, the force on the electron, so if there was an electron here, the force is going to be in the opposite direction. So this is actually the direction of the electric field here. Okay, and since the charge is negative, F is QE, so the force on the electron will be on the opposite direction. So this is going to be 1.6 10 to the minus 19, the magnitude, times 0.05 newtons per coulomb. Okay, and when you do that, you find that the force, the magnitude of the force is going to be 8 10 to the minus 20 newtons. Okay, so this is the Q times E. All right, clear? So if this question asked for what is the induced electric field inside, if the question was the induced magnetic field inside, let me try to do that. So let me change all of this. All right, so now we're going to choose a point P inside. So let's assume point P is somewhere here. Somewhere here. So this is now R. So I will take my loop here. This is radius R. Okay, and I will write Faraday's law is the derivative of the flux with respect of time. Okay, so this will simplify to E the times the integral of ds, which is the circumference of the circle, which is 2 pi r. Okay, this is going to be equal to the flux. So now the flux is going to be, this is the flux here. So this is the area. So this is going to be pi r squared times the derivative of the magnetic field with respect of time. Okay, so the pi's will cancel. The square here will cancel, and we will obtain the electric field is going to be R over 2 times the derivative of B with respect of time. So this is going to be R over 2 times 8 t squared minus 8 t. Sorry, 6 t squared, 6 t squared minus 8 t. And so you replace also t at 2 seconds, and you will get the magnitude of the electric field. Okay, so this is how we can apply Faraday's law, general Faraday's law, and which says that a changing magnetic field will induce electric field. So notice that at this point the electric field is induced even though there is no magnetic field here. The magnetic field is only in this region, but because the magnetic field is changing, it's inducing an electric field. It is here and also inside here. Okay, any question about chapter 30? Yes, 30. Any question? Please, this is you need to practice this, and you have a homework. When is the homework due? Sunday, isn't it? Is it? There is a homework already posted for this chapter. Okay, so now we're ready to move to the next chapter, and So this chapter is chapter 31. We're going to be speaking about inductance. And for those who are in electrical or computer engineering, we spoke about resistance, capacitance. This chapter we are going to speak about inductance. So first of all, we'll speak about self-inductance. Okay, we'll speak about RL circuit. Unfortunately, we're not going to do RLC circuits, even though it's covered in the chapter. We will speak about energy stored in a magnetic field. Like we had energy stored in electric field for capacitor, we will see that also we can store energy in a magnetic field in an inductor, and we will close by speaking about mutual inductance. Okay? Yes? سمعتك؟ بكرة؟ Tomorrow night. Okay. Okay. So, yeah, I can maybe extend it. Tomorrow we have the quiz, so I will extend it maybe Friday night. Okay, so let me start the presentation mode here. right. Okay, so we have seen in the previous chapter that a changing magnetic field induces an EMF. Okay, if you have a circuit, it induces an EMF in that circuit. It induces an electric field even if there is no circuit. So here, let's consider this is a circuit here. So it has a resistance and it has a switch here and a battery. Okay, and notice that if I close the switch and the current is going to start flowing, and we know that currents generates magnetic field. So the current, remember, current flowing will generate a magnetic field, and we can use, so it will generate a magnetic field. Now, this generated magnetic field is going through this loop. So what's happening when we close the switch, the magnetic flux is going to be changing. This magnetic flux that is changing is going to induce an EMF that is opposed to this change. So here, if we draw, this is a magnetic field coming out of the page. So this is the existing magnetic field here. Okay, so it will, this changing magnetic field, it changes the flux through the circuit, so it will induce a magnetic field in the opposite direction. Okay, this magnetic field in the opposite direction, that means there will be a current. So this is like this, so it's going to be in the opposite direction. So if you point your finger and you swing like this, so as if it's generating an EMF opposed to this current. This is what we call the self-induced EMF. Okay, so this is a self-induced EMF. Okay, and so the current increases with time after the switch is closed. There is an increase of magnetic flux through the loop of the circuit that creates an induced EMF in the circuit, and the direction of the induced EMF is given by Lenz's law, is such that it would cause an induced current in the loop, which would establish a magnetic field opposing the change in the original magnetic field, as we have illustrated here. So this is now increasing, so it will generate a magnetic field in the opposite direction. Okay, so the direction of the induced EMF is opposite to the existing EMF, which is the battery in this case, and this results in a gradual rather than instantaneous increase in the current. So that's why when we close the switch, and if you connect, for example, you connect an ammeter here, or an oscilloscope, you will not see an immediate switch. You will not see, so if you turn on the switch, you will not see the current suddenly jumping like this. You will see that it will actually be a gradual change, okay, because of the self-induced EMF. The induced magnetic field here, the changing flux produces an opposite effect, or it's called back EMF. It will oppose the change and it will slow down the increase in the current. Okay, so this is what we usually refer to as the self-induction. This effect is called self-induction because the changing flux through the circuit and the resultant induced EMF arise from the circuit itself. So here we don't have external magnetic fields, we don't have magnets, we just have a circuit. But just by throwing the switch to close the switch, the current is increasing. When you close the switch, the magnetic field is changing, so there is an induced magnetic field that will induce an EMF in the opposite direction. So this is often referred to as self-induced EMF because everything is happening from the circuit. There is no external magnetic field or things happening. So the self-induced EMF in a circuit is always proportional to the time rate of change of the current in the circuit. So we can write that for the self-induced EMF, which is, we can write E, the subscript L, is equal minus L. This is proportionality that is called inductance, times di dt, which is the derivative. Remember, before we have the induced EMF is minus d phi dt. Okay, so in this case, and we know that this flux is dependent on the current that is flowing through this circuit. So we can write this is minus LDI. In fact, we can write that this is equal to minus d phi dt. the changing flux through the circuit. Okay, L is called inductance of the loop. So this is inductance. So this is a new term. Okay, and it only depends on the geometry of we will see of the capacitor. We can find the direction of the induced EMF using Lenz's law. So it just opposes the change of the flux. Okay, and we can define the self-inductance difference VL across the inductor for an ideal inductor. So an ideal inductor is a solenoid usually that has zero resistance, and the magnitude VL is equal to the magnitude of the self-induced EMF. So here VL is equal to EL, which is minus L di dt, which is also equal minus the derivative of the flux. But since if we're going to use a solenoid, it will be minus N d phi dt. Okay, so here is a circuit with an N loop. So this is a solenoid. Okay, if we consider the closely spaced N turns carrying a current I, and we can write that the induced EMF EL, or the inductor EMF, is equal minus N d phi dt, which is equal minus L di dt. Okay, so notice from this we can deduce that L, so if you take the integral of both sides, we can deduce that L is equal N times the flux divided by the current I. So this is the inductance of a solenoid, can be obtained from this. Okay, so assuming the magnetic flux passes through each turn, and L is the inductance of the entire coil, so do not confuse between L as the inductance and L the length of the coil. So we will use small l for the length of the coil, okay, instead of capital L. All right, so this is the equation. L is equal N times the flux, the magnetic flux through the single loop, divided by the current I. Okay, the windings and the inductor are said linked by a shared flux. So this is the shared flux here. Okay, and the product N phi, okay, is called the magnetic flux linkage. This product here is called the magnetic flux linkage. The terminology is not very important. It's so we can say that the inductance L is a measure of the flux linkage produced by the inductor per unit current. So the flux linkage, so this is what we call flux linkage. This is the current I. So if you take the ratio of the two, it will give you the inductance of the solenoid. The unit for inductance is Henry, okay, and so if you here, let's see. Okay, what do we know? The flux, magnetic flux is B, which is Tesla, okay, and times the area. So this is meter squared, isn't it? So yes, B times, so Tesla meter squared divided by the current, which is coulombs per second, or amperes. Okay, and yes, we have to convert to Tesla to the SI units. So anyway, you will eventually find that 1 Henry is 1 volt second per ampere. Yes, 1 volt second per ampere. Okay, and so recall the resistance of is a flow of current. R is delta V over I, and here we can see that the inductance, if you take this here, okay, you can see that the inductance is minus the induced EMF EL, or the inductor voltage, divided by the derivative of the current. Or usually in electrical engineering, we say VL is equal L di dt. We usually forget about the sign. So VL yes, epsilon L is equal L di dt. Like I C dV dt for capacitors, the voltage across the inductor is L di dt. Okay. So the inductance is really a measure of the opposition to a change in current. Okay, so the higher the inductance, the more is opposition to a change in current, so it will increase exponentially at a slow rate compared to a small inductance. All right, so let's try to verify if we understand this. Here we have a coil with zero resistance, and it has ends labeled A and B. The potential at A is higher than the potential at B. Yeah? So VA is higher than VB. Okay, and this is the induced voltage EL, and you can see the direction. It's from A to B. Which of the following could be consistent with this situation? So which one of these here? So is the current constant and is directed from A to B? Is the current constant and is directed from B to A? Is the current increasing and is directed from A to B? Is the current decreasing and is directed from A to B? Or the current? So you can read. So choose. There might be more than one, by the way. So if the induced voltage is in that direction, in such a way that VA is larger than the VB, what do you think the current is? Is it what is happening to the current? Is it constant? Is it increasing, decreasing? Is it moving from A to B or B to A? So think about it. I'll give you half a minute to determine this. Remember, it's given by Lanz's law. Lanz's law says that the induced EMF will oppose the change. It's minus the derivative of the flux with respect of time. So obviously A and B are out of the question. لأنه if current is constant, there is no changing flux, and hence there is no induced EMF. So A and B cannot be. Now, so choose between C, D, E, and F. Okay, so who says C? Anybody says C? Okay. Who says D? The current is decreasing and is directed from A to B. D. 1, 2, 3, 4, 5. Okay. Who says E? The current is increasing and in the direction of from B to A. Okay. All right. And so this is the current is who says F? The current is decreasing and is directed from B to A. Anybody? All right. Well, it looks some of you are correct. So here we have actually two correct answers. All right. So we know the EMF is the induced EMF is in this direction. Okay. So the existing EMF so here. So let's take the current. If the current is flowing from A to B, if the current is flowing from A to B, the change in the current has to be opposite to what we have, the induced. Okay, so if the current is decreasing here, this EMF will oppose it and it will try to maintain it. So if the current is flowing from A to B, so from A to B and is decreasing. So if it is decreasing, then the EMF will oppose it and will be in this direction. Now, let's take the other situation. Let's assume the current is flowing from B to A. Okay? If it's flowing from B to A and it's increasing, this will oppose it. So if the current is increasing, okay, so the EMF is opposed. So now the induced EMF is going to be opposing the change. So the two correct answers are D and E. Okay, so in both situations, the induced EMF will oppose the change. So how can we have an induced EMF in that direction? So if the current is flowing in this direction and is decreasing, it will be from left to right. It will oppose that. or if the current is moving in this direction, but it is it's moving in this direction and it is increasing. Okay, so it is increasing, it will oppose the change, so it will be from left to right. So this is actually not an easy conceptual question, determining the direction of the current and how it's changing. Okay, let's do this example. Consider a uniformly wound solenoid having n turns of length L. Assume L is much longer than the radius of the windings and of the core of the solenoid is in air. Find the inductance of the solenoid. All right. So now we have seen an equation before that says EL is equal minus L di dt. Okay. And we said this is equal to minus the derivative of the flux with respect of time. Okay. So let's determine what is the flux through the solenoid. So remember, if we have a solenoid of n turns and the length L, okay, so the number of turns per unit length is small n, we determined that the magnetic field is mu 0 n I. Let's use capital N I. Okay, so we can write that L di dt. Okay, so from this equation we determined that L, so here I forgot N. Okay, so L is going to be equal the flux linkage divided by the current I. Okay, so we needed to determine the flux. The flux is going to be N times B times the area. So this is mu 0 and I times the area of the, so this is the cross-sectional area here, A, so let me keep it just as area A, divided by the current. So the current will cancel and we obtain L is equal to mu 0 capital N times small n times the area A. Okay, I don't want this, I want, okay, so let me write N divided by L is equal to small n, so we can write that capital N is NL. Okay, so I can replace this. The inductance is mu 0 times NL n squared L times A. Okay, so if the area is A and the length is L, the volume of the solenoid is equal L times A. So I can write that the inductance is equal to mu 0 n squared times the volume. So this is the volume of the solenoid. So notice that the inductance of a solenoid is only dependent on the number of turns per unit length, which is characteristic of the inductor, and is equal and dependent on the volume of the inductor. So you can use any of these equations. I can also write that small n is equal to n over L squared. So I can write this here, L is equal to mu 0 n small n divided by L times A. So it will be mu 0 n squared L times A. So any of these equations will do. Okay, and so you can I probably this is one is the easiest to remember. Okay, so it's mu 0 n squared L A. If you have an inductor, if you know the number of turns per unit length, and you know the volume, you can determine. So you can use either this one or this one. So this one or this one. Okay. Next question. Find the inductance of the solenoid. Calculate the inductance of the solenoid if it contains 300 turns. Its length is 25. So we just plug in the numbers and calculate the self-induced EMF in the solenoid if the current carries. All right. So now he's asking us to determine what is a self-induced EMF in the solenoid if the current is decreasing. So here we just, since we know L, we can calculate this. We can determine EL is equal minus L di dt, and so this is going to be equal minus mu 0 n squared divided by LA times di dt, which is 50 amps per second. Actually it's minus 50 amps because it's decreasing, so it will be 50 amps per second. So this is the so let's look at the numbers here. All right. So this is the inductance. It's mu 0 n squared times the volume. L times A is the volume of the solenoid. And when you calculate that, you find this is 0.181 millihenries. And if you do the calculation of the induced EMF, EL, or the self-induced EMF, minus L di dt, it's going to be equal to 9.05 millivolts. Okay, so notice that it's not a big voltage, even though we have 300 turns in this case, or in the solenoid. So the induced voltage is not really a big voltage. Okay, so this is another equation, mu 0 n squared times the volume. All right. So the flux linkage, as we mentioned earlier, we can write. Remember, we said that it's equal to the flux linkage divided by I. Okay, and so here the flux linkage there is an LBA. Yes, so BA is equal to the flux, and capital N is small n. I think there is a mistake here. So BA is so here this should be small l and LBA. Okay, the magnetic field inside the solenoid is mu 0 and I. Okay, and so you end up with the same equation. So this is the same derivation as we had earlier. Okay, so this is equal mu 0 n squared times the volume. Okay, so you can use either this equation or this equation. Okay, so now we're going to, oops, we run out of time for the, but let me introduce this anyway. Here we have a circuit that is called an RL circuit. And so we have a battery, we have a resistance R, and we have an inductance L. Okay? And let's assume at time t equal to 0, we close this switch here. Okay? And we want to determine what is the Kirchhoff voltage law. So let's go into this direction here. Okay? So when we do that, we get the potential through the voltage. This increases, and let's assume the current is flowing this direction I. Then you are going through the resistance, so it's minus Ri, and then you're going through this inductance. And remember, the voltage through the inductance is minus L di dt. EL is minus L di dt. Okay, so this is now the equation, Kirchhoff's loop equation, and we need to solve this. So this is a differential equation because it has I and di dt. But if we play some mathematical trick, we can simplify this. So let's call x e over r minus I. Notice that in this case dx is equal minus di. And now we can replace this here term becomes x plus L over r dx dt is equal to 0. Again, this is a differential equation, and we can solve this differential equation if we can write this is x over dx. Dx over x. So we'll take dx over x here, and this is going to be equal L over r. Let's see. Yes. Yeah. Okay. So here, yeah. So dx over x is going to be equal minus r over L dt, and we integrate both sides. When we integrate both sides, we get the integral of 1 over x is log of x, and when we solve, this is the solution. So we replace this x in the equation here for I, and we get, this is now a new equation for the current I. So the current I in this case is an exponential increase. Okay, it's equal to the EMF of the battery divided by the resistance times 1 minus exponential minus RT over L. Remember, this is very similar to an equation we have seen before for charging a capacitor. Remember, we had